Thank you, Adrian. I'm going to talk about these advanced persistent threat campaigns that we've been hearing about for the past few years. It broke in the news with the Target and Neiman Marcus incidents a few years ago, and since then we have been hearing them repeatedly since in the last several years. So the question, so what happens in these attacks is that using techniques like spear phishing and advanced exploits, the attackers first get past the initial defenses, and then they get into an organization's network, and they stay there hidden for many months, even maybe a year in some cases. And so the question is, how can you sort of figure out when these campaigns are ongoing so that security analysts will have some way of understanding an ongoing campaign and have some real-time way to respond and take actions. So because they do get through the first-line defenses, analysts have to really rely on the second-line defenses, which are like intrusion detection systems and security incident and event management systems and so on. And so so one of the real problems is, of course, the needle in a haystack problem, because these systems tend to produce a large number of events, and the analysts can get lost. And even when they do spot one or two of the activities, they don't see the pattern, and so clues may be dropped because the whole thing doesn't seem to tie together into anything meaningful. So as a result, these kinds of APT campaigns often go undetected for a long time. So certainly people have been working on this area for a while. So intrusion detection has been an area that people have worked on for several tens of years. But still in a real world deployment, it's they are hampered by a higher false positive rates than what analysts are able to deal with. The second problem is the connecting the dots problem. Once again, there has been work going back to maybe even 15 years with the backtracker work, which was aimed at identifying, after some intrusion is detected, how do you go back, figure out where the attacker came in from, and how do you sort of figure out what is the full impact of the attack. And so there has been this work, but the real issue has been that this tool has been developed more like a forensic tool. So after somebody says and finds out that there's something happened on their system, then they can sort of do a sort of comprehensive analysis of what are all the things that could have gone wrong in their system. But what we want is something that's more of a real-time tool, where as the APT campaign is unfolding, the analysts will have something that they can act on in real time. So that's the kind of tool that we are trying to develop. So we want something that observes the system and provides some sort of a compact visual summary that an analyst can look at and then say, okay, so this is what is going on, so here's what I can do to stop this attack or respond to this attack. So the challenges I've already mentioned. So there's a large data volume and so on. So where I'm going to talk through the rest of the presentation as to how we overcome these challenges. So one of the problems with doing this type of work is, how do you get your attack data? And we are fortunate to that we had access to this DARPA transparent computing adversarial engagements. So essentially, they carry out these APT-like campaigns, and so there are two advantages there. One is that we don't have to construct the attacks ourselves. The second is that it, of course, keeps us honest, because we don't know exactly what the attack was. So we need to find the attacks, construct these graphs that show what went on, and then later on, when the ground truth is made available to us, then we sort of go back and we can say how well we did with respect to the ground truth. So this is sort of the overall architecture. We call our system SLEUTH. You can imagine it's a clever acronym. It's so clever that I don't seem to remember what exactly it stands for anymore. So so we take data from currently from 3 different operating systems. The way that this program is structured, there are research teams that are actually using this original raw data and giving it to us in a form that's operating system independent, so we can actually use it without having to parse audit logs and things like that. So right now we consume from Linux, Windows, and FreeBSD. For Linux, we get the data from the Linux audit daemon. For Windows, I believe the data comes from the Windows event tracing. And for FreeBSD, there's a system that's been developed based on the dtrace framework. So first, all of this come into the system, and we basically build a sort of a dependence graph. That's the input to the rest of the system. So one of the issues that we needed to face was how do you make this graph to be space efficient, because if you talk about a long-running campaign, you might be talking about audit logs that have hundreds of millions of events, if not billions of events. How do you represent all of that compactly in a way that you can analyze quickly? So once we have the graph, then we have our attack detection technique, which is based on tags. So we assign tags to files and processes based on where the provenance of the data that they are using, and using this provenance information and a set of policies, we are able to detect attacks. And once we detect the attacks, these alarms go off. Then we have this graph analysis technique, which can do a backward and forward analysis to basically construct the whole scenario and display it. Okay, so let me talk about what do we mean by detection using a simple example, which I would call as a micro APT example. So here's an example where the attacker is trying to insert a backdoor into some vendor software. So the way they are going to do that is they are going to replace some file that is always included, linked into every executable by a compiler. So what they do is that they first drop this file called crt1.o into the user's website. So essentially the user visits a website, and there's a drive-by download type of situation. This browser exploit basically drops this file in the user's directory. The problem is always that that's not enough, because the attacker really needs to put this in a system directory in order for the linker to compile it into every program. So this file, which is the user's home directory, needs to be copied into a system directory, which means that the attack needs root privileges. And you can assume that when people run browsers, they're not going to be running as root. So the way the attacker works is that they are trying to modify the user's bashrc file. The idea is, you modify the bashrc file to redefine the sudo command, so that the next time the user, say, installs some package, they say sudo apt-get something, and then at that point, the redefined sudo, in addition to installing the package, also copies this data into the directory /lib. And then ultimately, Alice comes in, and she wants to compile her code. At this point, this file gets linked automatically, and then you have this software with a backdoor. And to complete the picture, we will just assume that what this does is that whenever it runs, it's going to steal some confidential data. In this case, it's a password, and then sends it out. Right. So typically, you might expect that this second stage of the attack will take place on a different system, but to simplify our illustration, we just say it all happens on a single system. So the question is, how do we go through a scenario like this and figure out where the attacks are, and how do we construct the overall picture? So the red team actually carried out 8 exploits we had available across the 3 operating systems. As you can see, the scenarios ran for about a little over 3 days. In most cases, some of them are somewhat shorter, and you can see that in terms of the number of events that we are dealing with, they were in the range of tens of millions to a few millions to something less than a million in the case of Windows. So it all depends on how much background traffic the red team was running. So on Windows, they weren't running enough, running a lot of background traffic, so that's why the number of events is smaller. So the APTs have, if you look at some of these white papers on how on popular APT campaigns, they break down the stages of life cycle of an APT into several stages. There is a drop and load, which is the initial exploit. Then there are other stages like gathering intelligence, inserting backdoor, lateral spreading from one host to another, escalating privilege, and finally, stealing confidential data and exfiltrating it. And then when it's all done, there is often a cleanup phase, so that if the attacker finished their task, they can clean up and leave no record that they were even on the system. So the goal was to try to see whether we could detect all these stages. And as you can see in the red team evaluation, they try to exercise most of these stages of a typical APT campaign. So let me just go into, I'm not going to have the time to talk about how we build a compact dependence graph, but instead let me just talk about attack detection first. So the way we do attack detection is based on what we call as provenance tags. Okay, so you can think of these tags as like information flow tags. So we basically associate two types of tags. One is what we call as a trustworthiness tag, and the second one is a confidentiality tag. Okay, so trustworthiness tags, you can think basically there are two basic types of trustworthiness tags. Benign, meaning that you don't think this, you think this data is coming from a trustworthy source. Doesn't mean that it's, if you're downloading code from a benign source, it could still be vulnerable, but you don't think that it's malicious. Okay. Unknown means, well, it's coming from some source that you have no knowledge of, so it could very well be malicious, right? So it could be malware. So another important thing that we do is we divide up these trustworthiness tags into two parts. For each process, we maintain a separate trustworthiness tags for the code part of the process, and also separate one for the data that it uses. So what we find is that by doing the split, as I will discuss later, we are able to get a much better accuracy in detection. So the overall idea behind or the rationale behind our attack detection approach, I'll use the analogy of how if you from crime fighting. So you often look for motive and means, and in the case of in this domain, by motive, what I mean is that we look at the activity that's taking place on the system, and then we are asking the question: does this activity advance what the attacker is trying to achieve? Right. So does the attacker have a motive to do this? Right. So typical things are running. The attacker wants to deploy and run their code in order to, say, either create a backdoor or some kind of monitoring and exfiltration type of attack. Okay, or they may want to overwrite critical files, steal sensitive data, and so on. So these are what we call as motive. Then there is the means. Does the attacker have the ability to influence a particular action? Okay, so by putting the two together, we are able to build a system that is that's able to accurately zoom in on the real attacks without producing far too many false alarms. Right. So in particular, what we are able to do is we are able to build a detection system that doesn't require any training, right? And it's application independent, and also it's not based on some behavior that we associate with a specific piece of malware or anything like that. So it's not very easy for an attacker to manipulate the detector. Okay. So that gives you the rationale behind how we went about. So now let me describe the actual policies that use these tags and how they work. Okay. So untrusted execution means that there is some file which has an untrusted or unknown tag, and it's being executed. Okay. Now suspicious modification means there is already a file there which has a high trustworthiness tag. Somehow that's being overwritten with something that's of low trustworthiness. Okay. Then data leak. So there's an untrusted subject, which basically writes confidential data to the network, and untrusted execution preparation, which is like getting some piece of data ready for execution. So let's go back to our illustrative example and see how these steps work. So we have the initial step where the attacker modifies the .bashrc file. So benign file is being overwritten, so you have this suspicious modification. Later on, this file in /lib directory is being overwritten, and once again you have the suspicious modification. You have then this file is linked and an executable is produced. So now what you have is a situation where a file that contains untrusted content is being made ready for execution. So you have this alarm for this particular policy. Subsequently, it is executed. So you have an alarm for untrusted execution. And then there is this confidential data exfiltration. So you have a data link alarm. So the data leak alarm. So all those policies get triggered in this illustrative example. So we have a policy framework, a flexible policy framework, that allows an analyst to write these tag propagation and attack detection policies. So I don't have time to go through all of the details, but here are two examples that show exactly the tag initialization policy that we used in our evaluation. So the first rule basically says it's based on some kind of regular expression matching. What it says is that all pre-existing files as well as internet traffic coming from local addresses, they should be considered as benign, and anything that's coming from an unknown unknown internet site should be tagged as unknown and should be treated as untrusted. Okay, so we have these initial tag assignment, and as files get read and written and so on, these tags propagate, and it is these propagated tag values that we use in our attack detection. So that's a quick summary of our attack detection. So once again, you see that here are the number of events. So we have in the range of tens of millions of events in the case of Linux. And the number of alarms we produce is quite small, a handful of alarms in the case of untrusted execution and suspicious modification, many more in the case of data leak. So what we can say is that among all these, the first three columns here, there are I don't believe there are any false alarms, but there are some false alarms here. We haven't really investigated this 5,300 number to know how many are false alarms. And so what we have done in our analysis is that really much of the analysis is going to be much of subsequent analysis is going to be based on the first three columns rather than the last column. So the key point that I want to convey at the end of this particular summary is that even though there are millions of events, ultimately only a handful of alarms are produced. So I told you earlier about the fact that we split these tags into two parts, one for the code and the other for data. And what this is trying to show is that what is the difference that we get by doing this. And you can see that if we had a single tag associated with a process, right, then we would have many more alarms, right? Hundreds of times more alarms we would have, which means that most of the alarms, right? So essentially 99 out of 100 alarms that we produce would be false alarm, and therefore it will be difficult for analysts to do anything with it. But by having the split tags, we are able to reduce the number of alarms to a handful, and then the attacker can in fact track them down. The analyst can track them down one by one. So we also did a false positive analysis. So because a lot of our alarm detection is based on download and execute type of behavior. So what happens when you have a system where software is being downloaded and installed for benign reasons? So we did an experiment in our lab where we have a bunch of servers, and over a period of I believe 5 days, we enabled all the security updates, as well as the we manually installed like 100 packages, and we showed that with a simple custom policy that knows how software is legitimately installed, we can actually avoid all the false positives. So that's about attack detection. So the next phase is, once you have detected the attack, how do you actually do the backward and forward analysis so that you can build the whole picture, right? So backward analysis, the goal is you have an alarm, you go back and identify what is the entry point, right? So the entry point is typically sort of a network connection, okay? And there are many complications because there could be multiple entry points, there could be multiple alarms. So what we do is we essentially pose this as a graph reachability problem, and we have formulated it as a shortest path problem where the edge costs are based on the tags that we have defined. So what we say is that if you have an edge through which untrusted code propagates, then that is a more likely edge on which the attack took place than one where everything was benign. So here, green edges means it's all benign, red means either untrusted data or code, and because we prefer untrusted code, going back in this scenario from the alarm here, we trace back one step, so we go back to this. We go back on this path because this is a benign path, and then we go back there, and once again there are benign edges, and the red edges is what we follow, and once you're here, you could have two paths, but again the shortest path will follow here, and ultimately you identify that this is the entry point. So then once you find the entry point, then you want to go from the entry point forward and then identify where what all the attacker was able to get to, and once again we formulate this as a graph reachability problem using once again the tags to define the cost on edges. Okay, and going forward, so what happens is that now all these forward edges over here will become included, and then at the last step, what we do is there is a simplification step where we apply various criteria to determine whether certain edges and parts of the graph are useful or not. Essentially, we look for whether a particular vertex has interesting descendants, and if it doesn't, then we eliminate them, and once we eliminate, this is what we are left with, and this is the kind of thing that we want to be able to produce. Okay, so now with the real attacks, so once again these 8 scenarios, so the ground truth was made available to us in the form of what are the entry points for the attack, how many programs were executed, how many files were involved, how many exit points, and so on. And so we tabulated all of this information, and altogether there were 174 points that we needed to identify, and we were able to identify, I believe there were 175, out of which we were able to identify 174 correctly, and there were 15 false positives. So we looked at it in more detail, and you can see that there was just one case in which we had false positives. In the other cases, we were able to get all of them correctly identified. So this sort of shows you what a scenario graph looks like. So here is the attacker coming in. There is basically, you can see that this is the network address. This is the edges here are numbered, so they come in through here. Firefox then writes this file called Mozilla Nightly, which is then executed, and this looks like some program that gives the attacker remote access because it's getting a lot of data from network addresses. Then it launches a command shell, runs some programs, and again the whole thing repeats on this side. It runs a bunch of programs here which are supposed to represent information gathering, and then the data is sent out over here through another site. So this is a BSD scenario. This was a graph that was constructed from by scanning through about 5 million or 6 million events. So I must mention that this is so after our system produces a graph. We did some work to essentially lay this out in a more symmetric way so that it's easier for people to see. But by and large, this is exactly the data that our system produces at the end. Okay, so this is kind of interesting because this is an attack where there is no exploit. The attacker has already stolen some passwords, and they use the stolen passwords to come in, install a Trojan SSH server, and then carry out their activity, and we are able to capture all of those and show that in a compact graph. So this is the one constructor from Linux from 38 million events. This is the graph that we were able to produce. So in terms of selectivity, once again, what we find is that if we did the conventional backtracker type of approach, we would only be able to eliminate 1 in 5 events. Out of the millions of events, we'll be able to eliminate only 1 in 5. But by using the techniques that we have developed, such as using the split tags and the simplification, we are able to reduce this further by an impressive factor of 50,000, so that ultimately from millions of events you have a graph that now has tens of nodes. So performance is good because there are two things that you worry about: memory and runtime. So memory is what this shows here in terms of runtime is that a single, even though the scenario itself took 3 days to analyze it, it takes only like a couple of minutes. Okay, so there's a lot of related work, and I don't have time to go through them in detail, but they are described in the paper. So let me just very quickly go to the summary. So we try to develop techniques that a security analyst can use to understand an ongoing attack campaign and try to respond to it on a real time. We wanted to come up with an automatically generated visual representation that compactly summarizes the ongoing campaign. Okay, so the key point is that even though there were millions of events in an unknown environment, our system was able to really zoom in on the events actually involved in the attacks.